Okay, so grading of your PA1 is done. You're happy with the result. Please don't submit zip file because it's just one extra step for us, meaning Brad, to open that zip file, download it, and then find your information. You can upload as many files as possible in one submission. And right now, the files are not as big, so you don't have to zip them, okay? So for the next assignment, if you have 2 files to submit, just submit 2. Is there anything else?
No.
That was it, right?
Yeah.
Also, we're gonna post 2 of the better submissions for you to see what we were expecting. So you can go through the code, the style code, but since we already have your first submission, we know your style code. So don't just copy paste from someone else's code. We're gonna give you the whole M file, but it's just to help those of you that didn't know how to create the section and subsection for the public file. Right? Those of you that already knew, you're fine. Okay. I'm recording this. I'll have to share my screen. All right, so we ended up, here is my phone. I forgot to find my cheat sheet, so I have to look at my phone. So last class, we ended up on this problem, right? If you remember, and I wanted you to just go over it, think about it, how to approach. Now, before we do this, I'm gonna show you in general, if we have 3, 4 different frames, how do we relate one point, see one point from different perspective? Then from what you learn here, you're gonna go and solve the problem. All right, so I'm gonna give you a few minutes to do that on your own, and then I'll do it. All right, so let's say that we have a point C, well, P, and this is point P. We know the coordinate of C of P in frame C. All right, so this is a known value. Then we also know what is this transformation, TAB. We also know TBC. So when I say we know, you remember these were 4x4 matrices, right? We have those 4x4 matrices. So these are the information we have. The 4x4 matrices from A to B and from B to C. We also know the position of point P from perspective of frame C. All right. Now what we want to find is, can we find position of P from frame A? All right. So when I say we have TAB and TBC, do you think we know what TAC is? Yes. We know the relationship between them, right? So basically, I want you to think about from the known variables. What are the known variables? Those 3, and we have an unknown variable. If we can come up with an equation, a relationship that we can find the value for P for PA. Now, if I say PA is going to be TAC times PC. So remember, for rotation, if you wanted to find a rotation from a different frame, you write the rotation matrix from that frame pre-multiplied by the position of that point. Same thing for transformation. Transformation is just rotation and translation together. All right. So now, do we know what TAC is? Yes, what is TAC? So TAC is TAB TBC. You can always use this trick of canceling the subscript. So you make sure that that's what you have. You can also walk from this frame to this frame to this frame as if you're walking from A to C. So you have it. Now, if I replace this guy, then PA would be TAB TBC times PC. So here, I know what PC is, they gave me, right? We knew that was our known value. I know these two as well. So all you have to do is multiply these three. So you have 4x4 matrix times 4x4 matrix. What's the dimension of your PC? Huh? So a position is 3x1, right? But for this multiplication to make sense, what should it be? 4x1. How do we create that? Well, how to augment a one extra row for that position to become a 4x1 matrix? So for position, if you remember px, p1, pz, how do we augment this? We add a 1, right? Remember, for position, we add a 1. If it was a vector, it would add 0. That's why the 3 rotation matrix has 0 under that, all right? So you grab PC, whatever it is, you add 1, and now from mathematical point of view, you can perform this. And then once you get PA, what will be your PA? What's the dimension of your PA? 4x1, right? So how do we know what is the actual position? We need 3. So the last one is going to be 1, right? So the last one is augmentation. We take that out. The top 3 is X, Y, Z. So everything has to make sense. So you should be able to perform a mathematical operation here. All right. There might be, okay, so this is one way to approach this. Can you see another way to approach this problem? You're trying to find PC, PA, you're trying to find this. PA. We have PC. Are there other ways that you can find PA? Yes.
3x1 vector from OA to OB.
Let's say we only have this information. Yes.
Say the transformation from A to C multiplied by the vector.
That's what we have here. We already have that. You know, I thought you raised your hand. Okay. Yes. So you can't have TCA. It's like 2. Like if you go from one initial frame to the next frame. So if you have 3, it means that you went through 3 frames. So you will write it as TAB then TBC. So let's see, how about this? I want you to pay attention. If I write PB is TBC PC, can I write that? I'm not solving it right now. I'm saying that I could say the position of point P from perspective of frame B is going to be TBC, which you have, times PC, which you have, right? So you could also find P from P. So you actually have P from A in frame A, and you have P from frame B, right? So this is kind of like a middle between the line information that you have. You don't need it, but we could approach from this way. So now if I say PA going to be TAB PB, can I say that? Now, do you see what's happening? I can now replace this guy here, right? PA becomes TAB, so I'm writing this, right? TAB, instead of PB, I'm writing TBC and PC. So I got the same expression. Makes sense, right? But you see that there are 2 different approaches. Maybe you saw this first, you know, when you're solving this problem, or maybe you saw that first. Either one is fine, right? As long as you're using the information you have to find those positions. Now, I could have asked you what is the position of P from frame A and from frame B. You should have actually done both of those things. All right. Does this make sense? The whole operation, what we did here. So this is basically the basis that you use to solve this problem. Now, let's go over and see what are our known values, and what's the unknown. What is it that you're trying to find? Well, the question says express coordinates of P in frame A. So this is point P, this is frame A, so we want PA, right? This is what we want. Now let's take a look at the situation. What do we have? That's frame B, and then this is P in B. That's the position. So frame B sees P at those coordinates. This line here is the position of one frame with respect to the other one. So I'm going to call it P trans. How much one frame moved to go to the other frame. All right. And we are trying to find this value, which is P in frame A, correct? So frame, now point P is fixed. We know the position of P from B frame, correct? We want to know what's the position of P in A frame. We know the distance between A and B. Do we know the rotation between A and B? We can write that, right? That's another factor that we know. Now, so a rotation and a translation happened, and frame A went to frame B. We can write the homogeneous transformation for this mapping, for this transformation, correct? We just learned from here, if we want, for example, PA, right? So PA is, what is PA? How can I relate PA to PB? What's the transformation? TAB, right? So I have PB. If I can find TAB, I have PA. Now let's create and let's form TAB. So we know TAB is a 4x4 matrix. 0, 0, 0, 1. That's just the augmentation, right? Yes. TAB. You're trying to find PA. So you can do this. So you end up with PA. All right, I can use a different color to show the rotation. Okay, so I'm gonna write, so you're gonna have a rotation matrix here and a position here, right? This will create. So what is this rotation matrix? AB. And then this is the position of this, like frame B in from frame A, which we already have it. We call it P trans. So I'm gonna create those. I'm gonna say other known values. We have P translation, which is 0, 3, 1. We also know what RAB is. Did anybody find it? 1, 0, 0, 0, the second column. The third one. -1. Z is in negative Y direction. It's a negative number. So you should be comfortable writing this by now. Yes. So you have frame A. You also have frame B. You remember the cosine direction and then of the projection method? That's how we find. So for example, C just says, look at X of B. XB is in the direction of XA and the other two are 0. So it's 1, 0, 0. Same for B. So you should be able to completely see this and drive this. Now we have RAB. I'm going to place it here. 1, 0, 0, 0, 0, 1, 0, -1, 0. Now, how about the translation part? So 0, 3, the translation or the distance between how much this frame moved to the other one is 0, 3, 1, which we were given here. So this was our known. And I already augmented them by the last row. So last row remains the same. So we have TAB. We also have PB. All we have to do is to multiply these together and find PA. Now, if you do that, let me be lazy. So PA is going to be this multiplied by PB 0, 1, 1. This is 3 by 1. We need it to be 4 by 1. So I will augment it by 1 because the position, I know that's how I augment it. You will get 0, 2, 2, 1. Now, this is not quite PA, right? PA is 0, 2, 2. And you have that. You did that, you think? You did it, it might be a mistake. Oh, it's that's not negative. All right. Yeah.
Why do we always augment it by 1?
So that's how we augment position. So here, let's say that we are this. So then we can create this one.
So it should always be 1.
Yeah, it always be 1. So this last column is always going to be like that. So these 3 are vectors, right? The vectors will get 0 for augmentation. Position gets 1 for augmentation. Always. So those, the last row is always fixed. And it has like mathematical background. It's not that we only use it in robotic, we use it in general in math. So we are borrowing something from math here. All right. So we saw that a transformation could be a rotation or could be a translation or could be both of them, right? So we just saw in the previous example, we had rotation and translation. Now, basic or pure homogeneous transformation are 6 of them. 3 for translation, X, Y, Z direction, and 3 for rotation on X-axis, Y-axis, and Z-axis. So these are your basics. You can always combine them, all right? But you should know their form so you can use them every time you see, oh, there's a rotation about this and a translation. Then you put these 2 matrices together. Now, if you look at translation, you see this? So translation about X-axis for A, if we are only doing translation, what is the rotation? If one frame is translating about along X-axis for A, what was the rotation that happened here? So 0 rotation identity matrix, right? So this first 9 represent an identity matrix. So if you have pure translation, as in this 3 basic, you're always going to have identity on the rotation part. Now, this is the X, this is Y, this is Z, translation along. So if you have translation on X, Y, and Z, but no rotation, all 3 of those get values, but this stays still identity. Make sense? So these are like, you're looking separately, but you can always mix them. You're basically adding them together. Now, if you had pure rotation, so if you only rotated, but I didn't translate anywhere, you will only have the translation, the rotation part, and as you see, the translation remained as 0. Now, rotation around X, we already knew. We're just plugging the rotation matrix. Same for here for about Y and about Z, right? Now, if I have a rotation about X and alpha, I also have a translation about Y-axis. How do I change that first matrix? There's a translation of B around Y, about Y-axis, along Y-axis. All you have to do is put a B here. So you have that rotation and you're introducing that translation. Okay, so these are 2 things that we are building, putting together to represent our transformation. All right. So this is a good slide to keep handy for your further study. I'm going to keep that like this. All right. Okay. The same as rotation, if you, because you might have different multiple transformation. If it's about the current frame, it's post multiply. If it is about the fixed frame, it's pre-multiply. Same rule. So you just need to remember that R is the same as rotation. Now, to see it, basically, these are two different examples. So I'm not expecting this to look like that or not. Two different examples to graphically show you this transformation about fixed axes or current axes. So this first case is current axis. So we are going from the transformation is from S frame here to B prime is going to take us here. All right. So whatever TSP, since this is, sorry, fixed axis. Fixed axis. So make sure I'm not lying to you. Yes, fixed frame. So for fixed frame, the transformation is pre-multiplied, right? So TSP is the transformation that we currently have, and we are going to rotate and translate. So rotation happens, then translation happens. But because it's fixed axis, it's going to get pre-multiplied. So the first one is, as you see, the rotation. The second one is a translation. This is showing translation. Now, if we go here, so the rotation was this one, translation. This is our the current transformation that we already have. It could be like 1, 1, 1, 1. Now you see that is pre-multiplied. So first rotation pre-multiplied, then the other one is pre-multiplied, right? So we get, sorry, just like rotation, we just write this. Now, for translation, you have to have a 4x4 matrix, right? But you're not rotating, so it will be identity matrix, and in the position you'll put the translation. For the next one, that's rotation, you have rotation matrix, there's no translation, so you can put zeros. And then when you multiply them all, you will get your final transformation. All right? For the current, this is current axis. The only difference is this is post multiply. So here, this is a separate example. Translation is happening first. Just because of this, I can tell. And here is the rotation. 2 rotation is happening. But since it's going to be post multiply, so this is 1, this is 2. Post multiply. Okay. Same as before, you just have to use those basic rotation transformation matrices. All right, good. So do this example. So show the homogeneous transformation matrix T for these 4 consecutive transformation. Rotation is not rotation. All right. And you can write the T total as, I don't know, I'm going to T1, T2, T3, T4. So you can leave it as 4x4 matrix. You don't have to actually multiply all 4 of them. All right. I want you to write out what is inside the 4x4 matrix for each of them. Yes. Let's see, hopefully we will not sleep. If you finish this and you're confident your answer is correct, I encourage you to go to the next example and do that one. I wrote the first one, and since all of them are current axes, just post multiply them. So if this was T2, T3, T4, this is a translation, X and E. This one, translation Z and D. And then this one is a rotation Z and theta. So all you have to do, go grab those pure transformations and plug these in and then write them. I'm just writing the T total. All right, what if this one was this last one? So yes, what if okay, the things that you want to keep handy at hand, the rotation is the transformation. You already know by now. Pre and post multiply. You also need to know how to calculate the inverse. All right. And what is the inverse of the rotation? The transfer. You have a couple of things that you need to remember to be able to solve the problem. Now, if you're all done with this and you're good, go to the next example and try to think about what you can ask and try to solve, and I will start that in a minute. But make sure that you got what happened here first. Next example is your first actually robotic looking example. So, hopefully what is this question? So many numbers? You're a computer guru, so you like just like typing crunching numbers, keyboard. Yeah, we're gonna use pen and pencil. Guess what? When you get to use MATLAB, then you will say, oh my God, really appreciate that you're doing that. Let me use MATLAB. This is a mind game. Oh, you're trying to multiply them? You don't have to. No, this is the end of it. Stop here. Don't multiply them. They're not evil. Just stop here. Oh, that's why it's disgusting. Stop here. Okay, so if like if you didn't know the problem, I would ask you to use MATLAB to do all that. Don't need to. I'm sorry. Right? I said you know that. Okay. Yes. That's the thing. No, but do you know how to calculate the inverse? I need you to go and grab it. Okay, so if you're done with this, this is the example. This is your book example. If you want to go further, study it, but it's just the same thing. Check the numbers, you can. So we're trying to find the configuration of the object in frame E relative to end effector in frame C. So C and E right now look the same up there. This is, I need that glove, man. I need that glove. This is frame E, our object. This is the end effector, frame C. So let's say you have a robot, autonomous car or a car driving. There is an arm attached to it. There's an end effector that will grab objects. You have a camera in frame D. You have a fixed frame in frame A, and the object that needs to be picked up is in frame E. All right. So this is basically tells you why you learned everything you learned so far. So our vehicle is somewhere, doesn't know exactly where the object is, but it knows where the vehicle knows where it is with respect to fixed frame. It also knows where he is or she is or it is with respect to the camera. Camera sees the object. There's no camera on the robot. The robot doesn't know where the object is. The camera knows. The camera tells the robot that, hey, the object from my perspective is in this position. You know where I am with respect to your position, so go figure out the position of the object. This is what you're actually going to calculate. That's literally what you will be coding, right? So getting this sensor information and then calculate point B and go from A to B and try to grab. Now, of course, there's control going to happen from the end effector to grab that object, right? But we're not discussing that right now. We're trying to find point-to-point trajectory, let's call it. So you're going to find a point that says, hey, the object is in this position and orientation. Then the rest we'll figure out later. All right. So you also know all of these matrices. This is all you know. And you're trying to find what is TCE. So what is good to know what is TCE? What's inside TCE? So T transformation from the end effector to E to the object. What's in that transformation matrix? Why are we trying to find that transformation matrix? Anyone? Yes. Yes. You're trying to pick up on what's the information that is useful that's inside that transformation matrix. Rotation and position. So we get the position. For rotation, we get a matrix, right? 3 by 3 rotation matrix. We know there are ways to find angles polar angles, pitch roll yaws, axis angle, then you can tell your arm to go to those angles, right? So right now, we're just gonna suffice to find that rotation matrix and position. Okay, all right. Go ahead and try to write a few expressions to see if you can find CE. These are the things that we know. We are trying to find this. CE. We also know, hold on, what else do we know? TBC, we know this. TBC, EAD, TEE, EB, okay, we don't know this directly. That's Are you done? This is one way to look at it. There are other ways. So there are different ways to look at it. So what I'm writing is going to be just one of them. But you should be able to walk from one frame, go to the other, and write a loop for this one. No. No, no. Okay, do you remember the inverse of a transformation? I want you to write that in there. Actually, tell me what's the inverse of a transform. No. R transpose negative R transpose P 0 and 1. So for rotation, R inverse was R transpose, right? For transformation is not. Now, what you put yourself through is to find 2 times the inverse. There's easier way, but that's not wrong, but you just have to find 2 inverses. But there might be another way you can just directly do that. Not quite directly, but your answer is correct. That's what it is, right? Yeah. I don't confirm the numbers because like if I plug it from there, but that will be one way. So the inverse, we don't directly just transpose. We have to find the rotation time, transpose that, and then for the position, transpose of the rotation times the position, and then the negative of that would be. But it's not just okay. This is the inverse of the 4 by 4. So here it's not just inverse of a 4 by 4 matrix. It's a little bit more complicated. So you'll follow this.
Oh. Yeah.
Oh, wait, this is what I had with like what?
Yeah.
So one way to do it, I'm gonna start and then you can continue that or follow what I'm doing. So one way is that I can write TAB, TBC, TCE, because I'm trying to find TC, right? I'm gonna put that TC in a loop. Could be, so going from TAB, there's B. Oh, this big one. Going from car to the camera, okay, and then from no, from car to from the fixed frame to the car, and then from car to the end effector to the object should be equal to TAD from this fixed frame to the camera and from the camera to the object, right? Because they're both showing the where the object is. So if you cancel them out, they're both A to E. So this is another way that's different from what you've done. So we could take this walk. We could also then visit what you did, all right? So that's one way we could walk and say from this frame, from fixed frame to camera and camera to object, what the camera sees is, since the object is where it is not moving, is equal to, if you were going from the fixed frame to the robot to the arm to the camera, they're both end up at the same place. They started at fixed frame, they end up at the same frame. Now, things that we need to find, so I need to find this. So this is my unknown. Now, how many things we have already? We have TAD, we have TDE, we do have TBC. I don't have TAB directly. Okay, so how about this guy? Can I write an expression for TAB? Yes, can you tell me what that is? So TAD, TDB, right? And I have both of these. So I actually have TAB. So I can replace that in there. So this is one way to look at it. So what you have might not be wrong, because there are different ways of looking at this. So I can say, I'm gonna replace it TAD, TDB, then TBC, TCE is TAD, TDE, right? This is still unknown. How can I find this unknown? I have everything else. I can bring this to the other side, right? So TC, oh, not DC, TCE. CE is equal to, okay, how do I do this? So this has to be inverse, right? Where does it go? Does it go pre or post of the other side? So I have, so I want you to pay attention to this. This is AD, TED, TD, sorry. This is the right-hand side. If you're getting the inverse, this will go pre-multiply. All right, so now you just plug in all the values. So the difference between this and what you did, you had to do twice the inverse. That's two different methods. I did the inverse one time. So I won't say it's easier or more difficult, just one approach. Yes.
Why does it come up?
Math?
Yes.
Yes, math.
Okay.
You remember AX equal to Y, to find X is A inverse Y? Also has to, you have to think about, I think, dimensions or math. But yeah, this goes back to the algebra. Yes. I didn't show TDB there. Yeah. Oh, I didn't show that. Where did I show TDB? Oh, okay. Sorry. I was just trying to show what matrices you have. Thank you. So all you have to do is plug these values. It's in your book. And I already also wrote it in my annotated version, which I'm gonna post. I'm not gonna take your time of just typing those things, but I'll tell you what you will get. What is your final matrix? So your TCE would be 0, 0, 1, -1, square root of 2, square root of 2, 0, then square root of 2, negative the square root of 2, 0, 0, 0, 0, negative 75, negative 260. Derek, now I think this is disgusting. Okay, so what's the position of this? So this means that end effector has to move in X, Y, Z direction on following this. So this is position or X, Y, Z that the arm, the end effector has to move. Now to grab that object, to be in the position of the object, it has to also rotate. How? Because the element of this is not all identity. If it was identity, I know that it didn't have to rotate, right? So this has to rotate. Now I have a rotation matrix, right? Doesn't look, it doesn't quite look like what I'm used to see, but looks like some rotation about an axis happened there, right? Now, this is the inverse kinematic problem. You have a rotation matrix and you have to find the angles that get there. You choose your method and you find your angles. You want to go by Euler method or Fitch-Broglie or axis and angle. You just have to, so you can actually find the axis and angle for this one, right? You have theta and then you have the k, so k is k, y, k, z. But the thing is, for this robot, you have to see what joint is on the wrist. Is the wrist able to rotate around any axis or it has restriction? That's why you pick if it's gonna be Euler angles or roll pitch yaw or just axis angle, right? So this is the problem that we solve later. But basically, this is what you would do. So you get here, and then from here is how do I move my actuators, basically, what angles to get to that orientation. Make sense? So hopefully this example brought everything together, that why we're doing what we're doing. Okay. Next class on Friday, I will talk about exponential coordinate to wrap everything up. And then Monday I'm not in town, so no class on Monday, yay. On Wednesday, we start forward kinetics. All right, okay. You guys have a good day, and girls. Don't forget your class participation is due by Friday class time. So this is your class participation. There is no passport, so it's just an assignment.